Good morning, students. Welcome back to my 20th lecture of your subject code C701 of Environmental Engineering. Today I will discuss the module 6. First, I will start the module 6. What is the module 6 of your syllabus? That is the water distribution. So, pipe distribution network, analysis of the pipe network system, that will be first discussed in the water distribution, because in my previous lectures we have discussed on the water treatment. Now after the water treatment, water has to be distributed to the end users, and this water distribution will be taken place to the piping network system. Not only the piping network, the water distribution network, that is supplying the water to the end users. Now that has to be taken in mind, that the user that water has to be supplied as per the demand by the end users and the adequate pressure. And the three major components in the water distributions are taking place, that is the pumping stations, the storage tanks, and the distribution piping. Now, the systems are designed according to the loading conditions, that is pressure and demand at nodal points in the pipe network. Now we will deliver the analysis portion of the network system. That means the flow when we enter into the pipe network. Now each and every pipe system, which pipe will the flow against which the piping section will be designed. So we are very much interested to know the water flow in the different pipes in the network system. So that analysis I will definitely deliver in today's lecture class. That will be the focus. That is with the objective of the today's lessons. We will discuss, that is the analysis of the pipe distribution network. For that analysis, before starting that analysis, some basic primary things I must highlight. That is the Hagen-Williams equation. The Hagen-Williams equation regarding the piping flow, which is V equal to 1.318 C R to the power 0.63 S to the power 0.54. This is the Hagen-Williams equation, where the V is the average flow velocity, C is the Hagen-Williams roughness coefficient, and R the hydraulic radius is the bed of the slope. That is the slope of the pipeline, laying of the pipeline. The equation can be in terms of the head loss. If you see, the equation can be transformed into HL equal to KLQ whole to the power 1.852 divided by C to the power 1.852 divided by D to the power 4.87. So in short, we can write K into Q to the power 1.852. Now there is another equation which is called the Darcy-Weisbach equation, which is basically predominantly used in analysis of the network piping system. And I will describe here the Recross method, which is a trial error process for measurement of for determination of the flow in the pipe network. That Recross method is a very interesting method. The trial error method we will discuss how the analysis can be done in the pipe network to Recross method using this Darcy-Weisbach equation. That is the HL FL by D V square by 2G. Now if you convert V to Q by A, so ultimately A means pipe V square by 4. So it will be converted to HL equal to 8 FL by pi square G D square Q square. So in short, it can be written as K into Q square. That means the 8 FL by pi square G D square is termed as K. Now the friction factor is known, L is known, pipe length, D is the diameter is known. So the K constant value is known according to the constant of the pipe corresponding to the pipe. So K is depending on basically the length and diameter of the network of the system. Because F and G are constant, G is acceleration due to gravity and F is the friction loss. So that is the friction factor is constant for the pipes. But only thing L and D is changing, so that's why the K is changing. So K first we will determine depending on the L and D, and then we will find the head loss K Q square. So this is the basic equation, that is the Darcy-Weisbach equation I must highlight to you, which will be which will be used in solving the network problem of by the Recross method. Fine. Now, what is node? That piping network system I have just described. What is node? Node means the junction, that is the junction nodes are connection of pipes to transfer the water. The diameter of pipe is changed in these nodes. Fixed grade nodes is where pressure and elevations are fixed. That is the reservoirs and tanks, etc. Now, what are the valves? Valves are basically, these are used to vary the head loss or to control the flow. Now, tanks, this is the stores water and acts as buffer by storing water at low demands and releasing at high demand. So the pumps which are used as for increase the energy. So these are the system using the network system, the node, valves, tanks, pumps, etc. But when I'm going to describe the simulation of the network system, let me put an example of the network. That is it is a system of the, I mean to say, the 6 pipes and the 5 nodes. So here you can see the 6 pipes and a network system of 6 number pipes and 5 numbers nodes are there. So there are loop 1 and loop 2, 2 loops are formed. You see the incoming flow is 750 and the outgoing flow is 200 plus 350 plus 200, which is 750. That means what we can conclude here, the conservation of the mass and the flow has to be maintained in this pipe network system. What do you mean by the conservation of flow? That means the flow in should be equal to the flow out. That will be the conservation of the mass of the flow and conservation of the energy we are talking for this pipe network system. So here we can see the inflow is 750 at the node 1 and the outflow corresponding to the node 2, node 3 and node 4. If we summation, if we make a summation that 200 plus 350 plus 200, it will give 750. So incoming flow should be equal to the outgoing flow. So this is I'm showing you the conservation of the mass. That is the conservation of the mass flow at each junction nodes must be conserved. So this concept we must follow in solving in analysis of the simulation process in the pipe network system by the Recross method. And the conservation of energy means that for each loop energy must be conserved. That is, summation of the head losses should be 0. So if we consider a closed loop for a particular loop, suppose in this case there are 2 loops. So in loop 1 the summation of the head losses is 0. Again in loop 2 the summation of the head loss is again 0. Now head loss, what is the head loss formula? The head loss formula is already I have described you. Just to mention that what is the head loss formula, that is the Kq whole to the power 1.852. Now n is air, n is 1.852. This is the formula. Now again it is seen that sorry, if I follow the Darcy-Weisbach equation, then the formula is Kq square. That is HL equal to Kp into Q square. That is the formula of Darcy-Weisbach formula. That is Kp equal to HL equal to Kp into Q square. Now this is the formula. Now I am just going to the analysis part of the problem. Then it will be very much clear. Again, if you see the error, that means error means assumption in simulation process in trial and error method. First, you have to make an assumption of the flow in the pipe. After that, we will compute the error of the flow and we will make the correction to get the actual flow by the single trial or third trial or fourth trial. So, while calculating the correction, that is the error which you have to find out of the flow, then the formula will be expressed as sigma kq whole to the power n by sigma nkq whole to the power n minus 1. So this formula is derived. This formula straightaway will use. Just to mention that the flow distribution is assumed across the network. Then the correction delta Q as given in the equation 9. This equation 9 is very important because the correction part will express this equation applied in a particular loop, say P. The numerator in the equation N is algebraic sum of the head loss in loop P. Suppose for a particular loop we are considering the correction, then the numerator is the algebraic sum of the head loss of the loop P, that is Q to the power N. We know the head loss formula, and summation means the summation of the head loss, algebraic sum of the head loss in loop P, taking care of the sign of the flow. Assumption is if anti-clockwise positive, then clockwise negative. If you can consider the clockwise positive, then anti-clockwise may be negative. Then the corresponding head loss, the same is applicable while applying correction also. QP is added to the flows in the clockwise direction and subtracted flows in the anti-clockwise direction, vis-a-vis. Because the flow direction, whether it is clockwise or anti-clockwise, one if you consider positive, then another you have to consider the negative, and accordingly that has to be considered in the correction factor also. So this is the theoretical portion I am just describing. Once I will put the example, then I think it will be very much clear, because this is the analytical part of the solution of the piping network. So this can be understood only going to the example, only going to the solution, the sum, the numerical sum, the problem which I am showing you, only going to that solution of the sum, that is sum of the solution of this example. Then you can understand the realistic problem solution of this piping network. Now let me discuss one problem. The piping network, here two loops are there. How many pipes you can see? So 2, 4, 5, 6, 7 pipes. 7 pipes, 6 nodes and 2 loops you can see. You see there are six numbers, 7 numbers pipes forming the network. It's a rectangular shape of the network, and the 2 loops are there and the 6 nodes are there. So this pipe network you can see, but the friction factor is given as 0.2, and flow rate we have to determine, because in this lecture I will deliver how to determine the flow rate in simulation process in Recross method in the piping network system. That is the basic discussion. That is the purpose of the total discussion today in my 20th lecture. Fine. Now this is given in the question that 2.5 meter cube per second inflow occurs at the node A, and the outflow is inflow should be outflow, because conservation of the mass of the flow should be maintained in the network. That is the basic fundamental thing. So 2.5, if it is inflow, then outflow must be 2.5. Let us check from there are 3 nodes. Outflow is shown in the 3 node, C 0.5, D1 and E1. So if we add 3 nodes, 3 outflow, then inflow should be equal to the outflow, that is the 2.5. Fine. The 7 pipes forming the network, each pipe has the length and diameter that is given in the question. So if the length and diameter are given and the friction factor is known, then if we recall that equation, that is the Darcy-Weisbach equation, the famous equation which we will use for solving this solution. What Darcy-Weisbach is given? Darcy-Weisbach is given that HL equal to K, HL equal to KQ square, where K equal to 8 FL by pi square G D square. This is the Darcy-Weisbach equation. Now, knowing the value of F, L, D and G, corresponding K value, that means HL equal to KQ square. So K value can be found out. We know the F, we know the L, we know the G, D, pi constant. So we can calculate the K value of the Darcy-Weisbach equation for each and every pipe. So let us find out first the K value of that. What is K? K is nothing but, again I am telling you what is K. K is nothing but the 8 FL by pi square G D square. That is K. K is 8 FL by pi square G D square. So now, so the K value, just a minute, the K, what I'm telling, the K value, I can find out the For KB is 3.88, KBC is 6.89, KFE, KED, these K values have been found out corresponding to the value of L and D. Now you see, actually there are the L and D of different parameter. How many pipes of different L and D? 1, 2, 3, 3, then that means the here I can see the AB are different, fine, and BC is also different. But if you see the FE and ED, these pipe are same. Pipe are same means the length and diameter are same. So these two pipe are same. So FE and ED, if you see the FE and ED, that is KFE or KED will be same. So this is 5.06. Again, if you see A, B and CD pipe, that means AF, BE and CD, that three parallel pipes are each of 1200 meter length and 0.7 meter depth. That means their K value also will be same because they are all having the same length and diameter. So let us see the FA, EB and CD. FA, EB and KAF, KB and KCD each having equal value of 4.05. So practically there are the four values of K. One it is 3.88, another is 6.89, another is 5.06, another it is 4.05. Because three pipes are of same length and diameter. So this is the thing. So all pipes are of the same similarity pipe, that is the pipes having the same length and diameter considered as the same K value. So this is the thing. Now let us consider the solution part. When the K has been found out of each and every pipe, now consider the loop 1 and calculate delta Q. So loop 1 means in this loop I am considering, say this is the A, B, E, F. This is one loop. Again I am saying A, B, E, F. This is one loop. Fine. So if I consider 2.5 is inflow, let us assume that AB is 1.5 and AF is 1. Because if you consider AB is 1.5, then other is 1. Summation should be 2.5. Now this one, AF, again it is continuing in FE as 1 because same flow will come, fine. And in the flow of AB 1.5 assumption, let us consider 0.5 will be passing through the B. So balance 1.5 minus 0.5, 1 will be passing through BC. And what will be the exit? You see 0.5, 1.5, 0.5. So the outflow is 1. So ultimately from ED, it will pass through 0.5 only. And this 0.5 and corresponding to the 0.5 of the CD will flow out as 1 meter cube per second. So this flow balancing of the flow, first you have to make an assumption so that the balancing of the flow is occurred in your first assumption in the piping network. That is the first and foremost of your task. Now all the K constant values of the pipes have been determined. Now what is the formula of the delta Q? That is the correction. If you go to that equation, that is the sigma K Q square. That means summation of the head loss. So what is that? K Q square means KF QF square, KFE QFE square. So there are loop 1 I am considering first. So there are 4 pipes. So 4 K Q square will be there. Sigma K Q square means there are 4 pipes. So 4. Let us consider KF QF whole square. That means KF AF you will consider AF value of the AF, that is the K value of the pipe AF is it has been found out 4.05. So put the value of 4.05. Then what is the QAF whole square? That is the flow flow you have considered 1. Let us consider the anti-clockwise flow as positive. So 1 meter cube per second A flow, that is being considered as positive. So one consider 4.05 into 1 square. Next, when you talk about the FE flow, that is the FE means the next pipe of the loop, that is also against the anti-clockwise 1 meter square 1 meter cube per second. The flow is anti-clockwise, so here again it is positive. One is positive 1 whole square. And what is the value of KFE? KFE is 5.06. So 5.06 into whole square. Now coming to the pipe KBE into Q square. When we are considering the KBE, you see the clockwise flow has come in the loop 1. So clockwise means negative because you have very beginning you have considered the anti-clockwise is positive. That means clockwise is negative. So when you are considering the B pipe, that means 0.5 is the clockwise flow. That means it will be the negative. So minus 0.5 whole square into KBE is 4.05. Similarly, KAB, there also the AB pipe, it is clockwise, flow shown is clockwise, which is 1.5 meter cube per second. So it is negative because anti-clockwise is positive. So minus 1.5 into KAB square. So minus 1.5 into KAB means 3. Minus 1.5 whole square into KAB, that is KAB is 3.88. So numerator we have completed. Similarly, the denominator is the K into sigma of KQ. Sigma of KQ within bracket 2. Why 2? Because 1 by n air is 2. So since you have considered the Q square, Q to the power n is 2. So 1 by n, that is 1 by 2. And this is the sigma kf af, just linear summation will be there. Q into kf into sigma k q we have done in the denominator portion, and we have found out the 0.0187 is the correction in the loop 1. This is the correction we have found out. So again I am just recapitulating the thing what we have done. First step 1, we will find out what is the expression of the K. K is 8FL by pi square by GD square, and knowing the length and diameter of each and every pipe, first step we have calculated the K value, constant value of the pipe, which will be required for finding out the head loss of the loop. So that first step we have found. Step 2, then the assumption of the flow, that means in each and every pipe the flow balancing portion has to be done. The balancing of the flow in assumption of the pipe network, that process has to be done in the step 2. And what is step 3? Step 3, we have found out the correction applying that 1 by n k q to the power n by 1 by n into k q to the power n minus 1. N minus 1 means 2 minus 1 is 2. So k q square, summation of k q square is the numerator as q square. So 1 by 2, n is 2, and k q to the power sigma k q to the power n minus 1, that means k q sigma k q. So that we have done, and we have found out 0.0187. Fine. Next step 4, we are next loop, that means the same process will be continuing in the finding out the correction flow for the next loop 2. Let us consider the next loop 2 is what? Suppose we are talking for the portion of the pipe, that is the BE. B is the you see the B pipe. When you talk about the loop 1, then it is clockwise. But now solving the analysis part in the loop 2, then it has come in the anti-clockwise. So one pipe flow may be clockwise in the one loop, but it may be the reverse in the other loop, which is a common pipe. That has to be taken care. Again, I am telling the common pipe in the two loops. If one loop it is showing clockwise, then other loop it should be anti-clockwise. Like B pipe is a common pipe of the loop 1 and loop 2. While solving in the loop 1, we have seen that B pipe is a clockwise flow. So definitely in the loop 2, the B pipe should be, while considering in the loop 2, it should be anti-clockwise. Well, that's why it is positive. So plus 0.5 into 0.5 square into 4.05. Why 4.05? Because K EB is the 4.05. KEB is the 4.05 or KB. Fine. Next is I will go to the again ED. When we are talking for the ED pipe of the loop 2, then what is happened? It is the anti-clockwise flow, so 0.5 whole square, and the KED. What is KED? KED is 5.06. So plus 5.06 into 0.5. 5.06 into 0.5 whole square. Now, you see the BC, the clockwise, and CD also I am simultaneously showing both BC, the remaining pipes in the loop 2 is BC and CD, where it is both shown as clockwise as 1 meter cube per second and 0.5 meter cube per second. As both the flows are clockwise, that means it will be the negative. So as it is a negative flow, then if both are, you see the minus 4.05 into 0.5 whole square, minus 6.89 into 1 square, both are negative. Now the denominator pass is the sigma k into q, like 4.05 into 0.5. Same process what we have done in the loop 1, same process we have done in the q2, and we have found out the two corrections, delta q1 and delta q2 of the loop 1 process and the of the loop 1 network and the loop 2 network separately. Now the next iteration will be done. Now we have to correct the flows. So step 5, when we go for the trial 2, trial 1 we have made an assumption. Based on that we have calculated the correction, that is the delta q1 and delta q2. Now we are going for the adjusting the correction, and we will make the next iteration, that is the trial 2. Now QAF, let us consider what was QAF earlier. In our first assumption, QAF was 1, and what was the correction? What was the correction in the loop 1? That is 0.0187. So the correction is 0.0187. That means one flow we have assumed, and the correction is 0.0187. So 1 plus 0.0187 is 1.0187. Similarly, QFE is 1 meter cube per second. That was anti-clockwise positive, and the correction also it is positive 0.0187. So QFE has come that 1.0187. It has come. Now very interesting. I am talking now QB. While talking QB, what is the? This is the clockwise flow. So clockwise flow means it is 0.5. It is the flow we have considered. But here the correction will be negative because it is the clockwise. So here 0.5 minus 0.0187 has to be considered for the loop 1. But again, since it is a common pipe of loop 2, for loop 2 it is a anti-clockwise. So for loop 2 correction, it will be adding. So what correction it was? That 0.2088. So 0.2088 is adding. So this is to be noted. The common pipe of the both loop, some in one loop the correction will be negative, and in the other loop the correction will be positive, because in two loops the direction are the opposite sign, one in anti-clockwise and another is clockwise. Fine. Now what is QAB? QAB, the considered flow was, assumption flow was 1.5, and since it is a clockwise flow, so the correction will be negative. So minus 0.0187, so corrected flow is 1.4813. Again, if you see the QED, you see the QED, that means the second loop I am talking, QED is the anti-clockwise flow 0.5. So 0.5 QED 0.5, and for the loop 2, the correction was coming 0.2088. Since it is the anti-clockwise, so it has to be added. So corrected flow is 0.7088. Let us talk about the QCD. Now QCD is the clockwise flow 0.5. So correction to be subtracted. So what is QCD? 0.5 minus 0.2088. Now the remaining one only left, which is QBC. What will be the flow of QBC? Assumption was 1 and it is clockwise. So the correction to be subtracted. So 1 minus 0.208, 0.7912. So with this corrected flow, again the same process will be reiterated. So 2 to 5 trial up to the new, when the new flows will delta Q is insignificant, like delta Q is 0.0000 something, then we'll terminate the simulation. We'll consider that there is the end process of the iteration and the final flow will be calculated. So this is the thing that we have analyzed how to have, we have shown you, I have shown you how to analyze the closed loop network of the piping system using the Darcy Weisbach formula, using the head loss formula, considering the two main principles: the conservation of mass of the flow, that is incoming flow should be outgoing flow in the network system, and the closed loops, when you are considering the head loss of the independent closed loop is zero. From that we have derived that equation, and with that equation we have just found out the delta Q, the correction. I think this one problem will not suffix, so another problem will definitely clear much more idea, because this is the Recross method of the analysis portion by simulation method or trial method, rather I would say, for finding out the flow of the closed network piping system is very important as far as your syllabus is concerned. So definitely another problem we'll be discussing to give you better understanding, because this analysis part one problem is not sufficient. So definitely the next lecture, that is the 21st lecture, of this analysis part, again we'll be discussing another problem for solving the pipe network system, some complicated problem. This is a simplified problem I've shown you. Some complicated problem definitely I'll show you for further understanding of this analysis portion of the Recross method. So I will upload my lecture notes indicating what I have delivered to you, the analysis process of the closed loop network of the Recross method in the Google Classroom. Kindly have a glance through the lecture notes, and we'll be meeting in the live classroom. So there the one-to-one discussion will be there for clearing the confusion, for clarifications if any by the students like you. So it will be cleared, and further you will be meeting in the next lecture also the same type of some complicated problem will be solving for better understanding. So I will close it today. So thank you very much. Have a nice day to all.